Hello everyone. Today, for this thermodynamics course, we're going to do a little introduction to entropy. Take a look at these two pictures. This is the state at the beginning, state A, and then it evolves to state B. Initially, consider this a closed system with no energy or work flows across the boundaries. And the initial distribution of material in state A is as such. Then after some duration of time, there are gradients of this material, and it forms this big distribution where they're scattered throughout. Now, think about, maybe a cup of coffee. You get a cup of coffee, you add some cream to it, and the cream starts to diffuse around and move around, and then eventually the whole coffee cup is a well-mixed mixture of coffee with cream. Try to reverse that process. Try to go from this process to this process. It's not an easy thing to do. There's something that we haven't discussed yet in our mass and energy balance equations and derivations that drives this process. In the example of the particles here, this is provided by something that's called a gradient in the chemical potential, or that gives free energy. Another example system that we'll think about to motivate some of our thought on what this extra thermodynamic eventually we'll find as a state variable is consider two systems inside of a well-insulated container, and these two systems have a different temperature, maybe temperature A and temperature B, and so between the two, they are not in thermal equilibrium, but inside of each one, suppose everything is fast enough that there are no internal gradients and the temperature is uniform within each side of this. However, from left to right, there is no equilibrium at the beginning, and then allow the system to evolve towards equilibrium. Again, here we have nothing coming in from the outside to our system. It's well insulated, protecting these two systems from getting additional material information from the outside world. You could imagine this happening, and then you can imagine how hard it would be to make this reverse. The point of both of these examples is that there is another thermodynamic useful function. We'll start with theta, d theta dt, that captures the rate of change of theta in this system. And basically, this variable tends to increase in both of these examples, where there's a rate of theta generation in the system. So alternatively, we can say that somehow for the overall system we'll have d theta dt equals some theta with a dot on top, because that means it's per time times generation. As this system approaches equilibrium, we would expect this system as a function of time to increase in whatever this function is, and then eventually, as it's all spread out, there's no way to increase it any further. It'll reach some sort of maximum, so that at equilibrium we would expect this theta gen term to go to 0. Now what happens to theta overall on its way to equilibrium? You can see that it's increasing right here, and then eventually it plateaus at some maximum theta value. So basically, in mathematical terms, we can say that d theta dt is some variable that's greater than 0 away from equilibrium. Write that down here. But then d theta dt equals 0 at equilibrium, which means that the integration of d theta dt would become the integration of theta just being equal some constant value at equilibrium. It turns out in thermodynamics, this is a kind of a general wordy explanation of what we know and use called entropy. You may have heard about this as being a rate of increased disorder in a system or randomness, but we'll find that this helps solve many problems and conundrums. And so, with these motivating examples, this is going to be the beginning of our journey into entropy.